Okay, so where we left off was defining the unit electron volt. And it's defined as the energy of one electron when it's accelerated across a potential difference of 1 volt. So the difference in potential between these two plates, one would be positive, one would be negative, is 1 volt. And when we do work to move it across, then the electron's going to gain energy. Okay? And so remember, voltage is equal to work over delta over Q. So the work is equal to Q times V. The Q, we're defining 1 electron volt. Just before the video ended, I had written 1 joule here. But we're defining what's an electron volt. So an electron volt is the work done or the energy gained when a charge of 1 electron is moved across a potential difference of 1 volt. Well, 1 electron, we know its charge is 1.602 times 10 to the negative 19 coulombs, and voltage is 1 volt. So 1 electron volt is equal to, when I multiply 1 by 1.602 to the negative 19, I get 1.602 times negative 19. And a coulomb times a volt is a joule. And so 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So that's kind of like saying, 1 meter is equal to 100 centimeters. It's just a conversion factor that we're going to use. Okay? So hopefully now photoelectric effect makes sense. Let's think about what equations we have. Well, we have this one. Ek max is equal to HF minus WO, where Ek max we can find from that stopping potential. Maybe I'll go to a different... My thing keeps making it blurry when I put my hand in front. I'm not sure what its issue is. Okay, so we have the energy of a photon is equal to HF. We have the work function is equal to HFO. We have the stopping potential, VO, is equal to W over Q, but that W is really Ek max. Remember, it's the energy needed, the energy, goes back to this guy again. How big do we have to make the voltage to stop the electrons from coming across? So we find the voltage that'll stop even the biggest ones. Okay? So the stopping potential, so in other words, then you could, if you had the stopping potential, you could find Ek max. It's just equal to QVO. So these two lead to each other. Okay? And then the one other little guy that we have is C is equal to F lambda. And then we have our big one, Ek max is equal to HF minus WO. Okay? This one, sometimes you'll be given the wavelength of the light, and then you'll need to use the speed of light to find the frequency so that then you can use it over here. And remember, the speed of light is 2.9979 times 10 to the 8th meters per second. So let's do an example. Let's say that I'm going to shine light of frequency 6.2 to the positive 14th hertz on a piece of sodium in the photoelectric effect experiment. And the sodium has a work function of 2.46 electron volts. And so the question would ask, what is the maximum kinetic energy of the electrons? And it might say, in both joules and electron volts. Okay, so we're looking for Ek max, and it's equal to HF minus WO. So Ek max is equal to, H was 6.626 times 10 to the negative 34 joule seconds. F 6.2 to the 14th hertz. And most of the frequencies will be to the 14th, 13th, 14th, 15th. Most of them will be 14th. Minus WO. So our WO is 2.46 electron volts. And if you've been well trained with your units, you know multiplying these two numbers together, joules seconds times 1/seconds, will give us joules. You can't just subtract in this 2.46. You have to change it into joules. And so to change it into joules, our conversion factor is 1.602 times 10 to the negative 19 joules per electron volt. And when you multiply, the electron volts will disappear. You'll be left with joules, and then you can subtract. Okay, so 6.626 to the negative 34 times 6.2 to the 14th. The first term gives me 4.10812 to the negative 19 joules minus bracket 2.46 times 1.602 to the negative 19. The second term gives me 3.94092 to the negative 19 joules. And so then my EK max will be equal to 1.672 to the negative 20 joules. So the question said, what is it in joules and in electron volts? So to switch it to electron volts, to go from electron volts to joules, you multiply by 1.602. So to go from joules to electron volts, you would divide by 1.602 to the negative 19 joules per electron volt. Dividing, flip, multiply, you'll the units, and you'll end up with electron volts. So divide by 1.602 to the negative 19, and you get an EK max in electron volts of 0.1043695, etc. electron volts, which is a prettier number than something to the negative 20. And that's why we say, like, joules is too big of a unit when you're dealing with energies. Like if you were working in this field all the time, they would work more in electron volts, so they wouldn't have these negative 19s, negative 20s. Okay? All right, so there's an example. Maybe one more example, just because I have another 2 minutes. A photon of 8 electron volts falls on a surface with a work function of 5 electron volts. So in this question, a photon of 8 electron volts, that's EP. They're giving us EP is 8 electron volts. And then it says it falls on a surface with a work function of 5 electron volts. So it's saying WO is 5 electron volts, and it wants to know what EK max is. So if they're already, remember it's HF minus WO, but this 8 electron volts is the HF, right? This is just EP. So it's just 8 electron volts minus 5 electron volts. Whew, this is higher order math. So you get 3 electron volts. So we didn't have to change it to joules here because everything was in electron volts. If they give you the frequency, you're going to have to change it to joules, because you have to multiply the frequency by H, and H is in joule seconds. And so that's why up here we switched to joules. We had to, right? But down here, they gave us EP right off the bat, not the F, and so we can just subtract. We could then switch it back to joules if we want it by multiplying by 1.602 times 10 to the negative 19, so getting 4.806 to the negative 19 joules. All right, so now I'd like you to try on page 561, numbers 1 to 4, and on page 570, the problems, not the applying concepts, the problems, numbers 2 to 6. Okay? Thank you.